guys, here's our first video in Unit 4, Section 3, dealing with acids and bases. Now, you've dealt with acids and bases before, but we're actually going to tell you the chemistry behind it. So you'll need your notes, which is your pen and paper, tables K, L, and we'll also need table J as well. So make sure that you grab table J. And we'll also need to make sure that we highlight things. So grab some sort of colored pencils or highlighter to help you out with that. So for this lesson, we'll talk about acids, their definition, their property, some examples of them, and strong versus weak acids. We'll do the same thing for bases. Then the third thing we'll talk about are conjugate acid-base pairs, so we'll put them together in equations. And the last thing we'll talk about is water and why it's so special when it comes to acids and bases. So the basic definition of acids, well, there's two of them. One is the Arrhenius acid, the other one's the Bronsted-Lowry acid definition. Both pretty much mean the same thing, though. So for the Arrhenius acid, acids will produce hydronium ions, and hydronium, that can be found on table E if you need it. It's one of our polyatomic ions, and its symbol is H3O+. We can also say that it's hydrogen as well, or H+. So you'll see both hydronium and hydrogen being used interchangeably when we talk about these acids. So again, Arrhenius acid will say that hydronium or hydrogen will be emitted or released whenever it's in solution, and it's the only positive ion in there. The Bronsted-Lowry definition says that an acid is going to be a proton donor. Well, if we look at H3O+ and H+, we know that they each have a positive sign or positive charge, so they will be protons as well. So if you take a look at the bottom right-hand side of your screen, we have HCl, hydrochloric acid, being placed into solution, and you'll see that you have H+ and Cl- being mixed around in the solution. For acids, their properties. Well, you've seen the pH scale before, so let's kind of talk a little bit about it right now. One of the properties is that it turns blue litmus red. So let's look at the scale down at the bottom, and here we see that it goes from 0 to 14. From 0 to 7 is the acidic, 7 to 14 is the alkaline. And litmus is actually going to be an indicator. Now, you've used this back in bio. You may have used cabbage juice or pH paper or something like that. So with an acid, if you have a blue solution of litmus, it'll actually end up being red. And we can see that here from this chart. Over here, this acidic area is all going to be red, whereas the basic area will be blue. Acids can also be electrolytes, and we've talked about electrolytes back in Unit 1. So electrolytes will actually be able to give off ions in solution. We saw that with the H+ and Cl-, and kind of allow for conduction of electricity. Acids also have a sour taste, so when you think about biting into a fresh lemon, you can imagine that sour taste in there. And again, the acids have a pH of from 0 to 7. One thing that you may not have seen before is that it reacts with most metals. So let's take a look at Table J. This is the activity series. And this shows us how, pretty much like what happens in terms of which element is more active than another. So here, we'll scan through and find H. So H2 is right there, and we can actually base a lot of our stuff on acids and bases, like if something will react based upon H2. Now I do want to note H2 is not a metal, even though it's found in the metal category, and they tell you down at the bottom as well. So pretty much if anything is higher than H2 on table J, it will react. If it's not higher or it's lower than H2, then that metal will not react with an acid. So some examples are from table K. We have HCl, hydrochloric acid, HNO2, nitrous acid, and so on. So most of these, and we've seen this before, actually begin with, begin with H's, and there. CO2 does not. Well, we'll see later on that H2CO3 actually ends up producing CO2, or that bubble in solution. And then we also have ethanoic acid. Ethanoic acid is also known as vinegar, and we'll see an H pop up right there. So the whole point of these acids is that they can break up into solution. So when you have hydrochloric acid, it breaks up into H+ and Cl-. HNO2 will break up into H+ and NO2-. HNO3 is H+ and NO3-. Let's see, we have H2SO3. That can actually have two ways of breaking up. It can be an H+ and, an HSO3 minus, and then that eventually breaks up into another H plus and an SO3 minus 2. I could keep going on, but you can kind of get the point that all of these acids will break up into solutions, so you'll end up having H plus as the positive ion. So here we'll talk about strong versus weak acids. A strong acid will dissociate completely, and dissociate just means breaking apart, so make sure you make a note on that for yourself as well. So again, these acids will break up completely. For example, HCl will break up completely into H plus and Cl minus. It's going to be a strong acid. And here are the 6 examples, the 6 strong acids that you'll see. And take a look at Table K. Go ahead and highlight at least these 3, the HCl, the HNO3, and the H2SO4. These will be your strong acids. And after you've highlighted down at the bottom, go ahead and note that that is actually a key, or make a key for yourself that those are strong acids. Weak acids, on the other hand, do not dissociate completely. So when we put in, for example, HF in a solution, we see that we have F minus, we have H3O plus, again that could be H plus, we'll use those interchangeably. But you'll also see here that you also have HFs still combined together, they haven't broken up. So only a few of them will actually break up into H plus and F minus, some of them will still stay on as HF. So that's what a weak acid is. It won't break up completely. Now we'll go on to bases, and you'll see some of this stuff repeating as well. So for an Arrhenius base, it produces a hydroxide ion, or an OH minus, as a negative ion. The Bronsted-Lowry actually has a different definition, so this is kind of why we need to have 2 definitions of bases: the Arrhenius base and the Bronsted-Lowry base. So the Bronsted-Lowry says that a base will actually take on a proton. So, for example, if we take NH3, let's go back. NH3, that's going to be an example of a base. We'll see that in just a little bit. We'll add in water to it. And remember when I talked to you about balancing chemical equations, I like to write out water as HOH. It's still the same thing as H2O, but you'll see here why we actually end up doing that. So what this base will do, the NH3, it will actually take on a proton. So it's going to take this H plus away from the water. That ends up becoming NH4 plus, and then OH minus is left over once that H moves over to the NH3. So this is why we need to have 2 different definitions of bases. So one of them would be, again, the Arrhenius base, where you have like NaOH producing Na plus and OH minus, whereas the Bronsted-Lowry base says that the NH3 is actually going to take on one of those hydrogens, or one of those protons. So let's look at the properties. We know that bases are also called alkaline solutions, so make sure that you make a note of that. We have acidic and alkaline. They're also going to be electrolytes, so they can conduct a current in solution. They feel slippery, so if you accidentally get a little bit of NaOH on your skin and you kind of rub it between your fingers, you feel that it does feel like soap. All right. Here it turns red litmus blue, so if we have red litmus paper, we can see here that this is the blue section. This is all going to be the alkaline, or the basic area. It has a bitter taste, and its pH is from 7 to 14. Here are examples of bases. They're all found on Table L. So we'll find that NaOH, for example, will break up into Na plus and OH minus. KOH is K plus and OH minus. Ca plus 2 plus OH minus here. And then we just saw for NH3 that actually ends up being NH4 plus and OH. And that was that special definition for Bronsted-Lowry bases. For bases, just like for acids, the strong bases will dissociate completely, or they'll break up completely. And here are your 6 strong bases. So the example here is NaOH. You'll find that NaOH breaks up completely into Na pluses and OH minuses. You won't find any NaOHs stuck together in that solution. Whereas Table L, the first 3 on Table L are going to be your strong bases, so make sure that you highlight that for yourself and make a key. Weak bases do not disassociate completely, so that NH3 is an example. In solution, we'll have the NH4, which we know it breaks up into, the OH minus, but we'll also see those NH3s still in there, right? Just like what we had originally put in. So that NH3 won't completely break up. You'll still find some NH3s in the solution. Okay, so now the next subsection is conjugate acid-base pairs, and we did discuss this with NH3 already. Now, when we see any of these acids, again, I always make the habit of making this HOH. It's still going to be the same thing as water, just written out a little differently. So for these conjugate acid-base pairs, we know that this hydrogen will be donated to NH3, and that'll form NH4+. So we know that NH3 is a base because it will accept a proton from water. That makes water an acid because water will give up a proton. Now let's look on the right-hand side. We have NH4+ and OH-. We also see that there is a double arrow. That double arrow means that it will go in the forward direction as well as the reverse direction. So this is a reversible reaction. So we'll look over here, NH4+ and OH-. We have to figure out here which one the acid is versus which one the base is. We know that OH- is a base because it will take on a proton to become water. And we see here that NH4 can be an acid because, hey, it has an extra H. So that extra H can get donated to OH. This makes OH a conjugate base, and I've abbreviated CONJ. And that makes the NH4, or the ammonium, the conjugate acid. Again, it's not the acid originally, but it can donate a proton to become a conjugate acid. Down at the bottom, it shows that over here on the left-hand side, NH3 has added on a proton to become NH4. And on the right-hand side, it shows that water has removed an acid to become a conjugate base. So when we look at conjugate acid-base pairs, we actually will connect up the base with its conjugate acid. So NH3 is the base, and its conjugate acid is NH4+. Water is the acid in the solution, and its conjugate base will be OH-. So it can flip-flop between the two. So that's what this is showing here. So again, the NH3 to NH4+, that's showing, this diagram showing that it can go between the two, and the acid, the the water, and the conjugate base of the OH- is over here on the right-hand side. So here we have H2SO4 plus H2O produces HSO4- and H3O+. So here we have to figure out which one the conjugate acid is versus the conjugate base, and to do that we have to figure out first what the acid is versus the base. Now we'll take a look at both sides of the equation. We can see at the end that water ended up taking on an extra hydrogen. So because of that, we say that water will end up being a base because it will accept a hydrogen. H2SO4, on the other hand, is going to be an acid because it will donate the proton to H2O. On the right-hand side, we see that we have HSO4- and H3O+. The H3O+ can't take on any more protons, but it can give off a proton. In fact, it will give off the proton to HSO4-. So since H3O+ is giving away a proton, we'll call that the conjugate acid. And the only reason it's called conjugate is because it's in the product side here. The HSO4- is going to be a base, in fact the conjugate base, again because it's in the product. HSO4- will be a base because it will go ahead and accept a proton. So here we have the acid H2SO4. Its conjugate base is HSO4-. So this is a conjugate acid-base pair. Right. And on this side, and I'll use the arrows up here, we see that H2O and H3O+ are also going to be a conjugate acid-base pair. So go ahead and try this one on your own. Let's go ahead and see what is going to be donating the proton versus accepting the proton. So here we'll see that H2O we have HCO3 minus and H2O. Over here at the end, we end up with OH minus. So we know that this water must have given off a proton to the HCO3 minus. So the HCO3 minus took on a proton, so that must be a base. The water must be an acid. Then over here, we see that we have H2CO3 and then OH minus. We know that H2CO3 will give a proton to OH minus to become the HCO3 minus. So since OH minus will accept the proton, it will be a conjugate base. And again, the reason it's called conjugate is because it's on the right-hand side of the arrows. That makes H2CO3 the conjugate acid. So we'll line them up. We have HCO3 minus and H2CO3 are the conjugate acid-base pair, and H2O and OH minus are the conjugate acid-base pair as well. So you'll notice that water can act as both an acid and a base. That's what we call amphoteric. So amphoteric, or some other chemicals can do this as well, but water is one of the more common ones. Again, it can act as an acid or a base. So when you put this into solution, you have water molecules in a glass. You have waters on the left and right hand, as your reactants, and one water will actually donate protons to the other water, making H3O plus and OH minus. We'll find later on that when we talk about pH scale that the more H pluses you have, the more acidic it is, the more OHs you have, the more basic it is. So here, you'll find that water is neutral because it's always giving off the same amount of H3O plus and OH minus. So to summarize, acids release H plus ions or H3O plus ions. Again, we'll use those interchangeably. The pH is less than 7. We'll use table K to identify them. And for bases, they'll release OH minus or accept H plus ions. Both definitions are acceptable. And the pH is greater than 7. We'll use table L to identify them. Make sure you know how to write out conjugate acid-base pairs. And we know that water is amphoteric because it can both donate and accept protons. So I will see you guys later. Have a great day.